All right. So, moving into cardiovascular. Now, as an emergency room nurse in the United States of America, unfortunately, I have a lot of experience with patients with cardiac alterations, be it congestive heart failure, be it cardiovascular disease because of blocked arteries, heart attacks, things like that. I've got a lot of experience with it. I would certainly say that cardiovascular, in terms of all the things we talk about in patho, is definitely one of my wheelhouses, so to speak. It makes sense to me. I think the structure and the function of the cardiovascular system is pretty easy to sort of visualize. Remember whenever we talked about at the beginning of the semester about how really to truly understand pathophysiology, I'd like you to be able to sort of close your eyes and see it happening as a movie in your head. I think it's pretty easy to do that with the cardiovascular system. And it's so important to our practice. How many of you already, in the short time that you've had clinicals, have taken care of some sort of cardiac patient? Yeah, like I said, in the United States of America. We're going to see a lot of it. And if you haven't raised your hand, you'll raise your hand in the next couple of weeks, I bet, before the end of the semester. And if you haven't raised your hand by the end of the semester, guarantee you'll raise your hand by next semester. It's just so pertinent to our practice. So keep that in mind. Keep that in mind as we're moving through the lecture today. All right. Here's your objectives. All right. So, the heart and the circulatory system. I just said it's super important, and it's super important to our practice. Why? Why is the function of the cardiovascular system so important to our patients? Throw out some reasons of why we care so much about the heart. What does it do? Pumps blood, very good, to the tissues. And why is it so important that the heart pumps blood to the tissues? What does that blood carry to the tissues? Oxygen, nutrients, yes, we're having high school science here for a second. Other substances to the cells, right? Other helpful substances to the cells. How about also removes waste products from the tissues, from the cells, back up into the heart to be pumped out and sort of released through the lungs, like carbon dioxide, right? So pretty important. And so obviously when we're talking about the structure and the function of the heart, we're talking about obviously how it works under normal, perfect circumstances. And that's what we're going to do today. So as long as you understand that, and as long as you have a firm foundation of what we discussed today, it's going to make it that much easier to understand what goes wrong in that MI patient next Monday, or in that congestive heart failure patient next Monday. If you understand what's supposed to be happening, you can understand then why when things don't happen, why it can so severely and intensely impact a patient. So that being said, the heart pumps blood basically through two separate systems. You can really think of our cardiovascular circulatory system as two separate systems, right? Two hearts, essentially. The right side of the heart, the left side of the heart. The right side of the heart is sort of the pulmonary circulation. So it's what pumps the blood to and through the lungs, right? And then the left side of the heart is the systemic circulation. So it's the part of the heart, or the side of the heart, that pumps the blood to the body, through to those cells, to those tissues that we just got done talking about. So really they're two completely separate entities. They're two completely separate systems that just happen to be sort of right next to each other in this organ. That being said, they are serially connected. What do I mean when I say that the right side of the heart and the left side of the heart are serially connected? What do I mean that these two pumps are serially connected? What do I mean? Yeah. Okay, right, good. So the input of one system is the output of the other, right? And the output of the other one system is the input of the other, and vice versa, right? So they feed each other, they talk to each other. So even though they're two separate systems, if something goes wrong on one side, eventually, because that's the output of that side is the input of the other, eventually you're going to impact that other side, right? I mean, that's just kind of an obvious sort of statement. Okay, so they do speak to each other. And again, remember a little high school science here. Arteries pump the blood away from the heart. Artery away. That's how I remember it. That's how I remembered it since I was a sophomore in high school. Veins obviously pump the blood toward. Now, arteries are usually oxygenated, right? What's the one artery in the body that is not oxygenated? the pulmonary artery, because it's the artery that takes it away from the heart, but it's taking it to the lungs, so it's yet to be oxygenated. Very good. Very, very good. All right. So here is just kind of a visual of everything I just said. You basically can think of it as the left side of the heart as one pump, the right side of the heart as one pump, and here in the capillaries of each organ and the capillaries of each tissue is where it sort of loses its oxygenation and becomes deoxygenated, becomes veins, and goes back up to the body. Okay? So there's a good visual there for you. Okay. So let's talk a little bit about the structure of the heart. The heart is about the size of a fist, which is really sometimes hard for me to sort of put my head around. Oftentimes I think of the heart as being much bigger than the size of the fist, right? But it is, and it lies in a space in our body called the mediastinum. Now, obviously you know where the heart is, but have you ever heard of the term mediastinum? Is that something that you're kind of getting more familiar with? Good. So it's kind of the space like sort of above the diaphragm and between the two lungs. So right in here, sort of diagonally placed within that mediastinum area. We know that the heart wall consists of 3 different layers. We have the pericardium, which is made up of parietal and visceral layers. So it's kind of the pericardium is sort of this double-walled membranous sac that encloses the heart. There's fluid, pericardial fluid in that cavity. Under normal circumstances, and again, we're talking about normal circumstances today. Under normal circumstances, there should be about 10 to 30 cc's of fluid in that pericardial cavity, in that sac between those 2 layers. And that fluid lubricates the membranes, allows for the membranes to slide easily and sort of gently over each other as the heart contracts and relaxes. Obviously, if we've got not enough fluid in that space or too much fluid in that space, what are we worried about? Did I hear that?
Well, there's too little friction.
Okay, so if there's not enough fluid, you have what we call a pericardial friction rub. Those 2 membranes actually rub up against each other and can be very painful and obviously detrimental to the contraction of the heart. What about if there's too much, like in the example of like congestive heart failure where there's fluid overload in the system? What would too much fluid in that pericardial cavity, that sac, perhaps do to the heart? What do you think? Yeah. It increases the pressure in the sac, obviously, but then also on the heart. It almost acts like a tourniquet or a rubber band around the heart and doesn't allow it to pump properly because of that increased pressure sort of bearing down on the cavity, on the chambers of the heart. Good. So that's important to know. Okay, so that's the sort of outside layer, the pericardium. Then you have the myocardium. By far, it is the thickest layer in the heart wall layers. Why? Why is the myocardium such the monster, if you will, in terms of its size with all the different layers? Why is that so big? It's the muscle, right? It's the myocardial muscle. Very good. It's composed of the cardiac muscle. It's the layer that provides the contractile forces needed to move that blood through those chambers, through the heart, and out to the body. Good. It's also where the electrical impulses that create that automaticity and that rhythmicity of the beats of the heart, that's where the electrical activity moves through as well. And then the endocardium is sort of the internal lining. So it's the inside lumen of the heart. Okay, yeah. You've probably heard about this before. You've learned these layers before. This is review. But who cares, right? Why do we care? Specifically, why do we care about the myocardium and that we know what it does and that we know where it is and we know its function? Why do we care as nurses? Why do we care so much about these layers? Who cares? Boring. You've learned it before. Why do we care clinically? Yeah.
When you're having like heart sounds that are different, or you know that your contractions are different, it's probably occurring because the pulses aren't moving across the myocardium.
Great. Perfect. And another way to say that is that an MI, let's say if someone's having a myocardial infarction, that damages those layers, that damages specifically the myocardium, and it might damage to these layers affect the heart's functioning. So I just said that's what makes the heart beat is the myocardium. So what if you've got dead tissue? What if you've got hypoxic, necrotic, dead tissue in the myocardium? Is it going to be able to beat? No. How's that patient going to be doing in the bed? Not good. Same thing if there's a section of that myocardium that's dead because of, again, say an MI, and that section that's dead just so happens to be the section that electrical activity is supposed to move through. Can electricity move through dead tissue? No. How's that heart rhythm? How's that rate going to be? Not good. So again, that's why we care. That's why we care about these layers, because when we are looking at our patient who is having some sort of lethal dysrhythmia or is having acute heart failure because their heart's not able to contract and create that contractile force, we're standing there as a clinician saying, there's something going on in the myocardium probably, right? That's why we care about this. All right, so we need to understand what these layers do and what they are so that we know next week when we're talking about alterations of where this is occurring in our patient. I hope that makes sense to you. Okay. Here's a picture of what we just talked about. Again, just to kind of drive this point home. Look how thick the myocardium is. Look what a big layer this is compared to the endocardium and the pericardium. Again, contractile component of the heart. That should make sense to you by looking at that picture. All right. Okay, who, sitting in their seats today, thinks that they have a pretty good understanding of the chambers of the heart, where they are, the flow of the blood through them, and we don't need to review it? Okay, let's review it. I was planning on doing it anyway. I just wanted to see your reaction. Okay, so let's talk a little bit about and sort of review on the board the chambers of the heart first. Let's start with it. We'll start with that. I need a volunteer to come up here and put a puzzle together for me. Who would like to volunteer? Don't worry, you're not by yourself. I'm here. Everyone else is here. You can phone a friend. Yeah, come on up. Come on up. We're going to do this together real quickly, this sort of review of the chambers of the heart and the different structures of the heart. Okay, now, I have never promised ever to be an artist, right? Or to draw things anatomically to scale. Remember that, please. But I have pieces here, okay? I've got all these puzzle pieces. All these pieces are pieces of the heart. If we put it all together, we'll put the heart together like a puzzle, okay? As I am talking about the chambers of the heart and as we're sort of discussing the sort of structure and function of them, I want you to find that piece and tape it up on the board for me. And actually, let's switch spots, because I think I'll have you do it kind of just right here in this sort of open space here. If you guys need to come over, or you want to come over later, that's fine. I understand it's hard to see. Okay, so first chamber of the heart, right atrium. And I also do have these color-coded according to oxygenated versus non-oxygenated. So right atrium. While she's finding that right atrium and going to put it up on the board for me, tell me a little bit about what the right atrium does as a group. What does it do? What's its function? Receives blood from the systemic circulation. Good. So is it oxygenated or non-oxygenated? Okay. Very good. The atrium is usually obviously smaller. I shouldn't say usually. It is smaller than the ventricles. The atriums usually have thinner walls than the ventricles. Why? They don't have to pump the blood very far. They pump the blood just from the atrium to the ventricle, whereas the ventricle has to pump it up and out. Right. So the muscle is much thinner in the right atrium. Very good. Doesn't have to pump against as much resistance either, so that's another reason why the layer doesn't need to be as thick. Good. All right, how about the right ventricle? Find the right ventricle for me and go ahead and put the pieces together for me. What does the right ventricle do? Sends blood to the pulmonary system, to the lungs. Good, very good. So sends blood to the lungs to get oxygen, and to be sure, the myocardium is thicker here in the right ventricle. Beautiful, doing good. All right, again, this is not to scale. All right, how about the left atrium? What is, well, I'm sorry? Receives blood from the lungs. So now we're talking about oxygenated blood coming back to the heart from the lungs. Good. Good. All right. Don't want to say anything quite yet. I don't want to get ahead of myself. Good. All right. Last, left ventricle. Pumps blood to the systemic circulation. Good. Now, it's normal for there to be a little resistance of blood flow from the atrium to the ventricle on both sides, a little bit, right? But it's truly the ventricles that have to pump against a lot of resistance to get that blood up and out. And to take it even one step further, the pressure that the left ventricle has to pump against is greater than the pressure that the right ventricle has to pump against. So of any of these chambers that have just been so lovingly put on the board, which one of these chambers is going to by far be the thickest in terms of its myocardial muscle? The left ventricle. Very good, very good. And I actually have kind of an exact sort of example for you here on the board of why that is. So the mean pulmonary artery pressure, so the pressure obviously that the right ventricle has to pump against to get the blood to the lungs, is 15 millimeters of mercury. The mean systemic arterial pressure, so the pressure that the left ventricle has to pump against to get blood out of the left ventricle, is 92 millimeters of mercury. So you can see obviously why the left ventricle's myocardium is several times thicker than that of the right ventricle. Very good. And then last but not least on this slide is the septal membrane. Now which one do you think that is? Very good. If you'd like to place that in its spot, I'd be greatly appreciative. Wonderful. Can you tell I'm the mother of a 3-year-old and a 5-month-old? Very good. You're off the hook. Thank you very much. Why is the septal membrane so important? Why is its integrity and its structure in that location so important? Okay, a lot of the electrical activity of the heart runs through that septal membrane. Very good. And what's another really big sort of function, if you will, of the septal membrane besides the electrical activity running through it? It keeps the blood from mixing, from going from the oxygenated side to the non-oxygenated side and vice versa. In 2 weeks when we talk about congenital pediatric defects in the heart, we'll talk about those septal membrane defects that actually do allow for that mixing of the blood. So again, that's why it's so important for the integrity of the septal membrane to be there. Good. Very good. So it prevents blood from crossing over, and it also is where the Purkinje fibers are housed that sort of give that electrical activity down in here into the deep, dark caverns of the ventricles. Okay? I'm sorry? Is there a question? No? Okay. All right. Any questions here? Review, right? Okay, thank you very much to my lovely assistant. All right, next, valves of the heart. Another victim. I don't have any puzzle pieces here for you. You get to actually use a marker. Who would like to come up now? You're not alone. Come on up. Okay, we know the actual structure now of the chambers for you. Now we're going to talk a little bit about where the valves are placed, okay? And again, why they're important and why the integrity of the valves are important. The first set of valves are the atrioventricular valves, and that consists of the tricuspid valve and the mitral valve. Where is the tricuspid valve? You can actually kind of like make a little like couple lines there to show where the door may be. The tricuspid valve is on the right side, and it's the valve between exactly the ventricle and the atrium. And then what's on that side? The mitral valve. Very good, very good. So it's during ventricular diastole, and whenever I say ventricular diastole, what do I mean? Do I mean relaxation or contraction of the ventricles? When I say diastole, relaxation, right? Again, the way I think of it is die. It's like the, I don't know, ultimate relaxation. I don't know. I don't know how these things get solidified in my brain, but diastole is relaxed. During ventricular diastole, the AV valves do what? Do they open or are they closed during ventricular relaxation? Are they open or are they closed? They're open, right, because it allows for that passive ventricular filling to occur while the ventricles are nice and open and relaxed and sort of accepting. So the valves are open, these valves are open when these are relaxing to allow for that passive fluid filling of the ventricles. Very good. So the AV valves open, blood flows in from the atrium. Then, as the ventricles contract and start to shoot blood up and out of the heart, what happens to these atrioventricular valves? They close. Why? Why is it so important for the health and the efficiency of these valves and for them to close? What does it prevent? Backflow, right. It prevents backflow from the ventricles back up in the atrium and shoots all of the blood up and out of the ventricles. Good. Okay, so that's sort of the integrity of the atrioventricular valves. How about semilunar valves? We have the pulmonic and the aortic. Go ahead and show me where the pulmonic is. Good. And then the aortic semilunar. Yep, very good, very good. So again, as the ventricles contract now, what happens to these? They open, right, because of the increased pressure in the ventricle, they get pushed open and the blood ejects up and out of the heart. Good. And very good. So these are closed during ventricular contraction. These are open. So they do the opposite. So when the ventricular pressure exceeds aortic or pulmonic pressure, it forces those valves to come open. Very good. And shoots the blood up and out of the heart. Very good. So does it make sense to you? And what I really want you to understand from this slide is during ventricular relaxation, what each set of the valves are doing. And during ventricular contraction, what each set of the valves are doing. Does that make sense to you? Okay, very good. Thank you. Thank you. Okay. Last but not least, new person. You keep thinking you're off the hook. Last person, promise. It's not painful, I promise. Come on up. Last but not least, the great vessels. Now I have puzzle pieces for you again. Okay. All right. Again, by no means are they sophisticated. All right, so the great vessels. So the first one we're going to talk about is the superior and the inferior vena cava. And these are a little bit abstract, so I'm actually going to show you which ones these are because they're these. Okay. One of them is the upper, one of them is the lower. You can tape them. You can maybe even just put like one here and then one coming from the inferior part of the body. So the superior and the inferior vena cava, and there's some tape right there for you. Tell me what they do. What it does. Brings blood back from the systemic circulation back up to that right atrium. Good, very good. So receives blood from the systemic circulation, enters the right atrium. Is it oxygenated? No, that's why I have it blue. Yeah, so you can just put like one coming up kind of behind the heart and then one going up into the right atrium. Oh, like that. I envisioned it to go like that. Yes. Yes. So the inferior vena cava comes up from the lower part of the body, the inferior part of the body, and the superior vena cava comes from the upper part of the body, so the head and the brain, and they both come together and feed into the right atrium. Okay, so here's my picture of that, sort of showing that. I know, sticky tape. So here's the inferior vena cava coming up from the lower part of the body, and it kind of goes behind. The reason I have it sticking here is that it kind of goes up behind the heart and dumps into the right atrium, right here where the superior vena cava does. Does that make sense to you, my abstract art? Okay. Okay, good. Then we have the pulmonary artery. Of what's left, which one do you think is the pulmonary artery?
The pulmonary?
Mm-hmm. Do you think?
Oh, because it's non-oxygenated.
It's blue, right, exactly. So the pulmonary artery is basically a artery that leaves from the, where does it? Right ventricle, and kind of branches off to go to each lung. Each lung gets its own sort of artery. So it leaves the right ventricle and goes to pick up the oxygen in the blood. Very good. So where do you think that goes? So it leaves from the, yep, exactly. It leaves from the right ventricle and goes up to the lungs. Very good. All right. Very good. All right, next great vessel, pulmonary vein. Where would the pulmonary vein sort of be attached to? What does it do? Brings oxygenated blood back to the heart, and where would that go? Right, exactly. So that would, you can just put it right there, yeah. It would just bring that oxygenated blood from the lungs. So, here are my lovely lungs up here, 1, 2. It drains that oxygenated blood back here into the left ventricle. All right, left atrium, sorry, good. And then last but not least, the aorta. Where's the aorta? Good. And that leaves, yeah, it's just kind of, they're all kind of superimposed on top of each other. That's how it is in the real life too. So it's going to do what? Right. It's going, that's the vessel, that's the artery that the oxygenated blood from the left ventricle pumps into that feeds the entire body, right? And I've got some little branches off of the aorta here to show you how it goes up to the top part of the body, so the head, the neck, etc. And then the rest of this sort of goes, the big branch here of the aorta kind of goes behind the heart and feeds the rest of the body, legs, arms, etc. I told you I'm abstract. Okay. Are we clear on that? Okay, good. Kind of put the pieces together literally and figuratively of this puzzle of what the heart does and what it is. Very good. By no means is that sophisticated, so this is. This is more of a sort of scientific, sophisticated version of what we just did with my helpers on the board. Thank you very much, you guys. Was that helpful to kind of review the chambers? And okay, all right, good. Good, good, good. Now, blood flowing through the heart during the cardiac cycle. Now we've refreshed ourselves on sort of the heart structure. Let's talk a little bit about how the blood flow through it during sort of one cardiac cycle. And what I mean by cardiac cycle is that a cardiac cycle is each ventricular contraction and relaxation that follows it. So that's one cardiac cycle. So boom, boom, 1. Boom, boom, 2. Right? So a cardiac cycle consists of both diastole and systole. That's 1. Right? So let's talk a little bit about the flow of the blood through the heart and then what is actually happening in terms of the mechanism of action, so to speak, or the phases of that cardiac cycle. So talk to me a little bit about, we just kind of did it, so I'll just kind of refresh your memory, and I'm going to write it up here on my lovely puzzle here. So the blood is going to come back from the body unoxygenated from the tissues, and it's either going to enter in through the inferior vena cava or the superior vena cava into the right atrium. Blood's then going to move into the right ventricle. I always do that. Then it's going to move up through the pulmonic arteries to the lungs. The blood's going to get oxygenated in the lungs. It's going to come back to the heart through the pulmonic veins into the left atrium, move into the left ventricle, to then get pumped up and out of the body through the aorta to the head, to the neck, to the arms, to the legs. Okay? That is the flow of blood through those chambers that we just discussed. Now, how does it do that? What is sort of the mechanism that occurs during that cardiac cycle? So let's talk a little bit about it, okay, as we look at these pictures. So the first step, or the first phase, if you will, of the cardiac cycle is atrial systole. Now, I don't want to confuse you because I just got done saying that diastole is relaxation and systole is contraction. Right. But whenever I say when I specifically say atrial systole, what's the ventricle doing during atrial systole? Diastole, right, exactly. And when we're talking in general terms about systole versus diastole, we're talking about ventricular. So when you hear it just said diastole or systole, just know we're talking about ventricular. The only time it's not that is when we specifically put atrial in front of it, okay? So during atrial systole, which means ventricular contraction, what's occurring? I should say in terms of blood flow, what's occurring during atrial systole or atrial contraction? It's pumping the blood from the right atrium down into the right ventricle. Good, and I have that written here for you. Atrial systole is ventricular diastole. Okay, so that's 1. Second stage, what we call isovolumetric ventricular contraction. So what I mean by that is whenever I say isovolumetric, I mean the volume is staying the same. So the volume is not going down yet in the ventricle because the contraction's not hard enough to actually pump the blood out yet of the ventricles. So it's early in that contraction. It's early ventricular systole. So you start to get the ventricles contracting and the pressure mounting, but not enough to actually eject the blood out yet. That's step 2. And I'm talking both on the right side and the left side when I'm talking about phases of the cardiac cycle. Step 3, ejection. So now you actually have so much pressure mounting in both ventricles that it does change the volume of blood present in those chambers because it shoots the blood up and out either of the pulmonic artery or the aorta. So that's 3, late ventricular systole. For a very, very, very brief moment in time, number 4 happens. And that is, for a very split second, all 4 sets of valves are closed. For a very split second. And that's number 4. Number 5 is what we basically have as passive ventricular filling. So what this means is now the ventricles have relaxed again. They've contracted. Now they're relaxing again, and ventricular filling, proper ventricular filling, occurs during ventricular diastole because they're relaxed and accepting to that blood that's simply passively running from the right atrium or the left atrium into the ventricles. That's 5. That's what occurs during ventricular relaxation, ventricular diastole. And I have that here. The AV valves are open, allowing for passive ventricular filling. So what I have here on the board is just kind of increased specifics, if you will, of what you see here on the PowerPoint. Okay? Then 6 is basically the start of the cycle again. So 6 is actually also /step 1. It's kind of the same thing, right? And I wrote that here on the board. 6/1 starts over again with atrial systole. Okay. Also known as atrial kick. I'm not forgetting your question. Let me just finish this and I'll come back to you. Atrial systole is also known as atrial kick. The reason for that is we just said that during number 5, the AV valves are open and allowing for this passive filling from the atriums to the ventricles. Then at the end of that filling, the atriums then contract. They have atrial systole. And so what they do is all the blood's been drained out of the atrium, goes out into the ventricle, then that atrium contracts. And basically the reason it's called an atrial kick is that whatever blood is left in the atrium after that passive filling of the ventricle, that atrial systole, that atrial contraction, squeezes it out and kicks that last remaining little bit of blood out of the atrium into the ventricle. Does that make sense? Okay, that's why it's called the atrial kick. It helps that one last little kick through the contraction of the rest of the blood in the atriums down into the ventricles. Again, what's on the board and what's on the PowerPoint are the same in terms of the numbers. I just have a little bit different wording or maybe some more specificity in one of the two places. Question? Right, exactly. That's why it's isovolumetric, because if you didn't have the valves closed during that period of time, when there's a small start of the contraction, you would get that backflow. Yeah, you would. So it's true that you actually have valves closed here and valves closed here for a brief moment because you don't want that regurg. You don't want that backflow of blood from one chamber to the next. The reason that I specifically mentioned it in number 4 is because we're talking about it in terms of ventricular, and there's so much more backflow that would occur during this ventricular phase than it would during the atrial phase. But you're right. Okay. Any questions about the cardiac cycle? Here is another visual, so to speak, of what I just said. So again, to be clear, this slide, the previous slide, and what's on the board is all the same thing. I have them numbered the same. I just want you to sort of see it in a different way or get some specificity in sort of different angles. Okay? Any questions about the cardiac cycle? Okay. Next, still speaking structurally. I want to say first, so we're going to talk about the coronary arteries for a second. I want to say first that blood in the chambers, it's kind of interesting, right? Blood that we just talked about flowing through the chambers isn't the blood that actually supplies the oxygen and nutrients to the heart cells, to the myocardium, right? That blood that's pumping through the atriums and the ventricles and then up out, is it actually nourishing the myocardium and nourishing the heart? No, it's not. It's simply being pumped. What is the blood? Where does the blood come from that actually feeds oxygen to the myocardium and to the heart? The answer is the coronary arteries, right? So it's kind of hard to think about, like, okay, the heart is 24/7 bathed in blood. These chambers are 24/7 in contact with blood, and that's not what's feeding them. Once the blood gets pumped out of the left ventricle and into the aorta to go feed the rest of the systemic cells and tissues, there's a very small branch right here-ish off of the aorta that the coronary arteries branch off of and runs back. All the coronary arteries then run back to the outside of the heart, to the myocardium and feed the outside of the heart. Okay? Does that make sense to you? Okay. So the origin of the coronary arteries is right outside of the aortic valve, so like right out here, and right outside of the aortic valve and left ventricle, so right in here, and it comes back and feeds the outside of the heart. Now, it's really important to also understand that coronary arteries fill, you're able to get blood to the coronary arteries during ventricular diastole. Why would that be? Mechanically and sort of, in terms of physics, why does filling and pumping of blood through the coronary arteries fill during diastole? Kind of confusing, right? Because I just said blood gets pumped up and out into the aorta during systole, during contraction. But why would it be important then for the blood to actually then come back to the coronary arteries and be able to fill during diastole? Why would filling of the coronary arteries work better during diastole? I saw a hand.
Because like where it's located at the biggest pressure point out in the systemic flow, that you need to have that completely filled before the rest of the flow occurs?
Close. It's actually even a little bit more simple than that. The reason that coronary arteries fill during diastole is because think of what happens during systole. The ventricles are contracting. Everything is tight. There's a lot of pressure in that muscle. So if you're trying to pump blood into those little arteries that feed that muscle, it's not going to be able to get in because everything is so pinched and tight and forced, basically, in that muscle. It needs to be able to be relaxed and decrease pressure for the blood to be able to get in and fill on the outside of those ventricles. Does that make sense, physically speaking? Okay, good. The ventricle has to be relaxed in order for the coronary arteries to be able to have least resistance for the blood to sort of run in and feed. Again, to be clear, what we have here on the board is a cross section. So we're like, cut the heart in half and we're looking right into the ventricles. The coronary arteries, picture putting the front part of the heart back on, and they would run sort of to the outside of the heart, right? To the muscle part of the heart. Okay, so to make sure that's clear. Sometimes it's hard to kind of visualize. Okay, let's talk a little bit about the coronary arteries themselves. You have coronary arteries that branch off here from the aorta and feed the left side of the heart. And you've got coronary arteries that branch off right here and come around kind of to the back of the heart and feed the right side of the heart. The left side of the heart coronary arteries is sort of mostly the left side of the heart is fed from something called the left main coronary artery. And that kind of branches off into the left anterior descending. So occlusion here would cause an anterior wall MI, so a front part of the heart MI, because that's where the left anterior artery is. It's on the front of the heart, the anterior side of the heart. And then you have the left circumflex coronary artery. It kind of circles around and goes behind. So if you're looking at my heart, the left anterior coronary artery would feed the front of my heart, and the left circumflex would sort of feed the back side of my heart. Okay? And then you also have a coronary artery that feeds the right side as well, the right coronary artery, RCA. This kind of gets both the inferior and so the bottom part and the posterior side of the right side of the heart. So again, you have your left anterior and your left circumflex feeding the front and back respectively of the left side of the heart, and you have your right coronary artery sort of coming over here and feeding the right side of the heart. Has anyone ever heard of, well, first of all, let me just say this. What happens if these coronary arteries are blocked? You get an MI. You get a lack of blood flow to the cardiac muscle, right? So when you hear of someone needing a bypass or having a 80% blockage, they're talking about blockages of one of these three arteries, right? So blockages of these by plaque, by whatever it may be, is what causes an MI. So again, this is not an unimportant slide. I swear to you, all of you will take care of at some point in your life a patient that's either had an MI or acutely is having an MI in front of you or is about to have an MI. You have to understand that this is why. Because they've got a blockage in one of these arteries that feeds the heart, feeds the muscle, feeds the heart. major, major damage to the myocardial layer if one of these are blocked, because this is what feeds the myocardium. Anyone heard of someone say that someone's had a heart attack and blockage of the coronary arteries, and they say, oh, it was a widowmaker, or they had a blockage in their widowmaker or something like that? Anyone know which arteries are blocked in a quote-unquote widowmaker? So it's usually both. It's usually the left anterior descending with also a blockage in the left circumflex. Circumflex. Why do I keep saying flex? Why is that? Why would a blockage in the left side of the heart, so a left side coronary artery, be more detrimental and perhaps more lethal, perhaps a widowmaker, as opposed to the right side of the heart? Why is a blockage to the blood on the left side perhaps more dangerous than a blockage on the right side? Because that's perfect. Because that's what supplies the left ventricle. If the left ventricle, there's something wrong with the myocardium, and it can't pump and contract, what's going to happen? There's no getting blood to the whole body, right? So that's a much bigger deal if the left ventricle is, under attack, so to speak, than if the right ventricle is under attack, right? Because the left ventricle is what supplies blood to the whole body. If the left ventricle is not working, sorry, right? We're not doing good, right? That's why a left circumflex or a left anterior descending blockage is perhaps worse than on the right side, because you're affecting the left ventricle, the powerhouse, the bulging bicep of the heart, if you will. Okay? Hope that makes sense to you. All right, and here is, again, I was trying to sort of tell you, like if you picture putting the front part of the heart back on and looking at how the arteries would run sort of on the outside, this kind of shows you just that. So see how these little arteries run and feed the outside sort of muscle part of the heart? That's what I was trying to get at. Okay. Yeah. Sure. You mean like right here from where they bifurcate from the aorta?
No, I mean when you have like a widowmaker or an MI, is a common place for there to be a blockage right where the veins kind of split?
Where the arteries kind of split? Yeah, where they get smaller. So where they sort of bifurcate and get really small and kind of feed into like little capillaries into the myocardial muscle, the smaller the arteries are, the greater obviously the lumen, the circumference gets smaller, so the greater chance there is for a blockage. Does that answer your question?
I just wondered if it happened farther up in order for there to be a bigger area of tissue damage.
Oh, you mean like on the left side that we're talking about? Like, oh, yes, I'm sorry. Like we're talking about the left anterior and the left circumflex? Yes. If there would be a blockage right there where those two branch off, you're in trouble. Yeah, good question. Because now you've got one blockage, but yet you're affecting two arteries. Is that what you kind of mean? Yeah, good thought, good question. All right. Thus ends our discussion regarding the structure of the heart. Let's take a break, and we're going to come back and talk a little bit more about more of the mechanics, so the conduction and the contraction aspect of the heart.